多镜照整块. So and here, the multi-collimator is like one instrument, and then what you can do is you can put the camera on these instruments, and then that instrument inside it, there are multiple collimator. So this illustration means that each of them is a collimator, which you can say well, should have some light, so emit some light. And then inside each of the collimator, actually on the top there's a cross. Here's a cross. So basically, what I'm trying to say is that it's an instrument, and then you put it on the bottom, and then there's a multiple collimator over there, and sometimes it's a cross, and sometimes it's multiple line rays of those collimator. So in those collimator, they will emit light, and then each of them they have a cross, and so when you put your camera on top of it, and of course at a certain location. And so this is where you put your camera and those light rays will go to will point at the front nodal point. This is another term that I haven't tell you about. So this front nodal point is called 前节. Okay. So basically, you can for now you can treat it as the perspective center. So that's the camera station location. So you put your camera over here, and then those light rays were pointing at your camera, perspective center. Sorry, they were pointing at your perspective center, and then go through your lens, and then shoot it to your image plane, and then create an image like this. So basically that means that if you have a camera over here and take a photo, then it could be the photo that you have. This could be the photo that you have. So like I said, it's an instrument, and when you put your camera over there and then take a photo, and here is one array of the collimator, and here is another array of the collimator. Okay. So and as you can see, it has some code name, and from A, B, C, D, E, F, G, and to M. So the corresponding, on the image, the corresponding location of those collimator is, for example, A, B, C, D, E, F, G, and so on and so forth. So the middle one, this one, G, is called central collimator, and it appears over here. It will appear over here. Okay. Okay, so in this case, basically what we can do later is we can use those collimator to find out, to calculate what's the focal length of this camera. Right? We can use those collimator and those locations on the corresponding location on the image, and to calculate their the focal length of this camera. So the question is how? How can we calculate that just from this image? We don't have enough information, but however, because the multi-collimator is created by us, so we can control what that machine is. So the idea of that is you can say the angle between each of the consecutive collimator is 7.5 degree. So here is 7.5 degree, and here is 7.5 degree, and so on and so forth. So each of them, they are like 7.5 degree away from each other. So in this case, if you take a look at here, for example, if I draw G, here is the perspective center, and here is the image plane. If you draw a figure like this, and here is G, and here is F, right? Here's G and here's F. And of course, this is perpendicular over here, and this one is 7.5 degree. This is 7.5 degree. And so, what we can do to calculate the focal length of this camera is, because right now we know the angle over here, and what we need is just the distance over here. If we can know, we can measure the distance on the image. between the G and F, then we can use very simple math to derive the focal length. Okay, this should be very easy. Okay, any question till now? It should be very easy. So, in this case, the first step actually is to calculate the EFL. So the equivalent focal length. So EFL is calculated by taking the average from average of the distance from the G, the center collimator, to the surrounding 4 collimator. So as you can see, GF is this one, and we have GH, GS, GT. So what are those collimators? So G is over here, F is over here, and also you have S, T, and H. So which means that the EFL is taking the is calculating, first of all, is calculating the average distance from the center collimator to its surrounding collimator, right? To take the average of that. So why do we want to do that? Well, to reduce the random error, because every time when you are measuring something, there's a random error, like we mentioned before. Okay, so the more information you have, then the lower the lower influence that the random error will cause you. Okay, so we have 4 information up here. Then why don't we just use that? So we take the average of this distance. Okay, and after we take later on, after we take the average, which means this 4 distance and then summation and then divided by 4, so that's the average distance. And after we have the average distance, then we can divide it by tangent theta, so which is the 7.5 degree. Okay, so in this case, you can calculate your EFL. So basically means that something like that. So your focal length is your distance over here and divided by tangent 7.5 degree. Okay. But here EFL not only consider just one distance, it's an average of the 4 distance. Okay. Any question to that? Okay. Okay, so let's move on. So in this case, you can have the equivalent of focal length. And with that, then you can estimate the supposed distance from the center collimator to any other collimator. Okay, again. So right now you have the focal length. And with this focal length, supposedly, because right now we know each of the collimator is 7.5 degree away from each other. So with this focal length, then we can calculate any distance from the center collimator to any of the collimator, right? Because right now, if this is if right now I want to calculate the supposed distance from G to H, then I can just use the EFL to multiply tangent 7.5 degree. And if right now I want to know what's the supposed distance from G to I, then I can use EFL to multiply tangent 15 degree, so on and so forth. So with the EFL, then I have you can say the ideal distance from the center collimator to any other collimator. So in this case, as you can see, what we can calculate is for different angle, 7.5, 15, and so on and so forth. We can calculate the supposed. Actually, this one is not this. Okay, this one is for measuring. Wait, let me actually write it down. In this case. Measure distance between G to others. take the averages. Right, that is the first step. Second step is calculate EFL. Right, so the first step actually is to measure the distance between the center collimator to any other collimator, and then take the averages. So as you can see, this average, the mean distance is the GFGH, GSGT, and take the average, and then you have the 1.183 over here. Okay, so and you can measure the distance from G to those four kilometers. That is 15 degree away from the G, and then measure the distance and then take the average, and so on and so forth. So this table actually represent the first step. And after that, the second step is to calculate the EFL. So as you can see, we use the 0.5 degree collimeters to calculate that, and then you can get this EFL over here. You can get this EFL over here. Okay, and then the next thing is, because right now we can use this EFL to calculate the ideal distance from the center to each of the collimator. So, for example, if right now we calculate suppose the ideal distance from the for the 15 degree, then it will be the EFL, the 153.305. This is the EFL, and we multiply tangent 15. So this is the ideal distance from the G to those 15 collimeter. All right, and then we also have a measured distance for the 15 degree. We have the measured distance for the 15 degree. So the differences between them, is minus 0.03 millimeter. This is called delta R, which indicates the length distortion, right? Okay. Right. So the third step, actually, we can go to the next page to have a table. Right. The third step is to calculate delta R with EFL. We can calculate the delta R with the EFL. So as you can see, the first row, that's the angle. The second row, the mean distance, that's the measured distance from the center collimator to other collimators. And the third row, the EFL, multiply the tangent angle. And this is the ideal answer. This is the ideal answer if you think EFL is the perfect, it is the final and perfect focal length. So the third row, that's the ideal distance. And the fourth row, the delta R, that's the length distortion at different angle. So which means the differences between the measured distance and the ideal distance. So these are the differences between the second and third row. Okay, that's the third step. Okay, till now, any question? If not, the next step is to calculate the CFL, calibrated focal length. And the calibrated focal length is actually defined by us. Right? Calibrated focal length is defined by us. This is a focal length that we try to get the best symmetry. Right? Again, this focal length is what we defined, and we assume that this camera can achieve the best symmetry. So what does it mean by symmetry? So as you can see here, for each of the distance, we have a different length distortion. and some of them they are negative, and some of them they are positive. So which means that on the image, some of them they are, if you are using the center as the radial center, if you are using the principal point as a radial center, and the density dissociation negative and positive means that some of them they are the density dissociation is away from the radial center, and some of them they are negative, they are closer to the radial center. So in this case, that's the behavior of here, the positive and negative of here. So, but right now we want to refine the EFL. We want to refine the focal length, so that we assume that this camera can have the focal length that can achieve that can achieve this condition, which is the largest outward density dissociation equals to the largest inward density dissociation. Okay, the maximum delta R, for example, right now is this one. Yeah, this one, right? Yeah, this one. So the positive 0.0633. So that's the maximum delta R. And right now the minimum delta R is this one, the minus 0.17. Right. So that's the minimum delta R. So which means that for the current EFL, if we calculate the density dissociation according to the EFL, then you have you at the 30 degree, then you have a point that is moving by 0.0.